Welcome to the video lecture series of solid state devices, course code EC301. This is the lecture of junction field effect transistor. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology, Kolkata. Contact hour 3 and credit 3. This is lecture 9. So this module actually consists of construction of JFET, field control action and characteristics of JFET, pinch of voltage derivation, numerical problem. The lesson plan here is field control action and characteristics and pinch of voltage derivation. So today we will start drain characteristics and transfer characteristics. So let us recapitulate a little bit the construction of JFET. This is high input resistance device, while the BJT is a comparatively low input resistance device. And if the channel is doped with donor impurity, then this is called N channel. If the channel is doped with acceptor impurity, then this is called P channel JFET. So N channel JFET have greater conductivity than P channel, as electrons have higher mobility than holes. So BJT is basically current control device. Why? Because base current is controlling the whole phenomena of bipolar junction transistor. So that's why, depending on the base current, the gain factor, the availability of collector current, all depends on base current. But FET is a voltage controlled device. As we have seen in our earlier lecture, that VDS and VGS, this voltage is actually controlling the phenomena of JFET. That's why this is called voltage controlled device. So theory of operation points to remember that gates are always reverse biased. The source terminal is always connected to the end of drain supply, which provides the necessary charge carriers. So here we will study the operating characteristics of JFET. So case 1, case 2, case 3, case 4. 4 cases are there. Case 1 is when VGS is 0 and VDS is also 0. That means gate to source voltage is 0 and drain to source voltage is also 0. Case 2 is when VGS 0 but VDS is greater than 0 or increased from 0. Case 3 is VGS is less than 0 but VDS equals to 0. Case 4 is when VGS less than 0, that is decreased from 0, but VDS is greater than 0, that means increased from 0. So let us start with case 1. When VGS is 0 and VDS also 0. In this case, drain current ID equals to 0 because VGS equals to 0 and the depletion regions around the P junction are of equal thickness and symmetrical. Now this is case 2. Case 2 is when VGS is 0 and VDS is increased from 0 but less than pinch of voltage, that is VP. For this purpose, JFET is connected to the VDD supply as shown in the figure. Here, the electrons, which are majority carriers, flow from source to drain, whereas conventional drain current ID flows from drain to source. Now, the gate to channel bias at any point along the channel is VDS plus VGS. that is the numerical sum of two voltages. In the present case, external bias VGS is 0. It is showing here. Hence, gate channel reverse bias is provided by VDS alone. Since the value of VDS keeps decreasing due to progressive drop along the channel, as we go from drain to source, the gate channel bias also increases accordingly. And it has maximum value at the drain gate region and minimum value at the source gate region. Hence, depletion region penetrates more deeply into the channel region in the drain gate region than the source gate region, as you can see here. This explains why the depletion region becomes wedge-shaped when VDS is applied. As VDS is gradually increased from 0, ID increases proportionally as per Ohm's law, and it is found that here you can see initially the characteristics curve follows Ohm's law. It is found that for small initial values of VDS, the N-type channel material acts like a resistor of constant value. It is so because VDS being small, the depletion regions are the large enough to have any significant effect on channel cross section, and hence its resistance does not depend on the voltage. Consequently, ID increases linearly as VDS is increased from 0 onwards. This ohmic relationship between VDS and ID continues till VDS reaches a certain critical value called the pinch of voltage Vp here. When drain current becomes constant at its maximum value called IDSS, this current is nothing but the IDSS, this is showing here. The SS in IDSS indicates that drain to source saturation current, or gate is shorted to source. Gate is shorted to source to make sure that VGS equals to 0. This current is also known as zero gate voltage drain current. It is seen from the figure that under this pinch-off condition, separation between the depletion regions near the drain region, if you go to the previous slide, the separation in the drain region reaches a minimum value. You can see here the separation reaches the minimum value and the width say W. It should, however, be carefully noted that pinch off does not mean that current is off, rather the current is maximum at this point. But this is called pinch off, that means minimum this amount of voltage is required to make it into a saturation mode. When VDS is increased beyond Vp, so what is happening? When VDS is increased beyond Vp, ID remains constant actually. At its maximum value, IDSS, here you can see that ID remains constant. It is due to the fact that further increase in VDS, that is beyond Vp, causes more of the channel on the source end to reach the minimum width as shown in the earlier slide. This region is minimum width, this channel region. But the channel width does not increase if we increase VDS, rather its length increases. As more the channel reaches the as more of the channel reaches the minimum width, the resistance of the channel increases at the same rate at which VDS increases. Or in other words, we can see, or we can tell that VDS is neutralized by increase in RDS. Actually, resistance is also increasing. So VDS is neutralized by increase in resistance. That's why it becomes this region, the current becomes constant as ID equals to VDS by RDS. This remains unchanged. Ultimately, a certain value of VDS is reached when JFET breaks down and ID increases to an excessive value as shown in the diagram. This is the breakdown region. And this voltage is called breakdown voltage, that is VDS max. So moving to the next slide, this is the enlarged version of this JFET drain characteristics. This is the VP, pinch-off voltage. This point is called knee point. From this knee point, it starts the characteristics curve. It starts to be non-linear. Before that, it is linear. But after this knee point, the characteristic curve becomes non-linear up to point B. And after point B, it gets saturated. And after point C, huge current flows through the device and the device junction breaks down. So this is the circuit of JFET. Gate source is shorted here and a positive voltage VDD is applied across the drain source terminal. A multimeter is connected, ammeter and voltmeter is also there parallel to the drain source terminal. This is the circuit diagram with shorted gate. So now we should concentrate to case 3, that is VDS equals to 0 and VGS is decreased from 0. In this case, as VGS is made more and more negative, the gate reverse bias increases with increase in the thickness of the depletion region. And as negative value of VGS is increased, the stage comes when two depletion regions touch each other. As shown in this diagram, this condition, the channel is said to be cut off. Particularly this point is said to be cutoff point. And this value of VGS which cuts off the channel is called VGS off. And it should be noted that VGS equals to VGS off equals to VP, that is minus VP actually. So VGS off equals to minus VP. And if we take the mod value, then VGS equals to VP. So we are getting that from case 3, that what is VGS off, what is the cutoff of the channel. And moving to the next slide, this is case 4, when VGS is negative, but VDS is increased. The same thing is happening here. VGS is more and more negative, but VGS is increased as shown in the previous diagram also. The values of VP as well as the devices breaks down and the voltage VB, actually this breakdown voltage at this point, huge current will flow through the device. Since gate voltage controls the drain current, JFET is called voltage control device. A P-channel JFET operates exactly in the similar fashion. Before that, we should go through this animation to make it clear to all of you. Here, gate voltage is decreasing from 0, or magnitude of gate voltage is increasing. It widens the depletion region, cutting down the current flow. After that, VDS is increasing. Small drain to source voltage increases the current. gate to source voltage is constant now. But at the same time, the depletion region width is also increasing. It widens depletion zone and limiting the current flow. That's why it is getting saturated in the characteristics curve after pinch of voltage. So moving to our next slide now. So if we summarize the matter, for negative values of VGS, the gate to channel junction is reverse biased with VDS equals to 0, that the initial channel resistance of the channel is higher, the resistance value is under the control of VGS. If VGS equals to VT, the device is cut off. The region where ID constant, the saturation and pinch region, it is called. And the region where ID depends on VDS is called the linear and ohmic region. So this is the JFET drain characteristics for different gate to source voltage. It is starting from 0, and if we increase the magnitude of the gate to source voltage, we will find that as the negative value is increasing, the current is gradually decreasing, as shown in the animation also, because the depletion layer width is increasing. So this is P-channel JFET has similar type of phenomena we can observe. Exactly in a similar fashion it reacts, except that the current carriers are holes in this case instead of electrons. Since only one type of majority carrier is used in JFET, they are called unipolar device, unlike BJT. So this is static characteristics of JFET, in which we have learned the drain characteristics. Next we will study the transfer characteristics of JFET. This is the drain characteristics of P-channel JFET. VDS is negative in this case, but for N-channel JFET, VDS was positive. And VGS is positive in this case, but for N-channel JFET, VGS was negative, just reverse of N-channel JFET. Reading material you can follow Milman Helkias or Donald Anyman. If there is any question, please feel free to ask me to this email ID. Thank you for your attention.